So, welcome back to our video lectures on projective geometry. We are dealing with conics, and this time I want to show you the very close relation from conics to projective scales. So a projective scale, you usually have it in a one-dimensional projective space, and this time we will learn that the line defining the conic can be considered as such a one-dimensional projective line. A little disclaimer at the beginning: throughout that lecture, all the conics that we will consider will be real and non-degenerate. So the conics we are dealing with are ellipses, hyperbolas and parabolas, and mostly I will draw pictures just with an ellipse. So let me start with something that we already had in one of our previous lectures. It's the following fact on the border between algebra and geometry. So if you have a conic and you have 4 points on a conic, and these points and the conic are assumed to be fixed, and you have one point E that is allowed to move on the conic, then it turns out that the cross ratio, how E sees the other 4 points, is really invariant of the position of E as long as it stays on the conic. So if I move that point around, you will always get exactly the same cross ratio for those 4 lines, and by that you see that well, if this point here moves around and the cross ratio does not really depend on the position of that point, it must be a property of the 4 points in relation to that conic, and we use that now to make a definition that we call the cross ratio of 4 points on a conic with respect to that conic, the cross ratio that we get if we view those 4 points from an arbitrary point E on the conic. And you can read that in different ways. First of all, you get a number that really relates 4 points on a conic, so you already get a glimpse of how the border of the conic here behaves as a projective line, because whenever you have 4 points on it, you can calculate a cross ratio. This really has a very strong taste of a projective line. On the other hand, we also saw that we can use this as a kind of definition of the conic curve. Whenever you have any 4 points, then the set of all points that sees those 4 points under a fixed cross ratio is exactly the conic we are talking about. So now we will really tighten this link between the line that defines the conic and a projective line. So before we go there, one little remark. I said that I can move my point E arbitrary on the conic. So in particular, it may happen that it coincides with one of the points, and in that case, at least literally, the join between these points is no longer defined. So if you assume that E is at point D, there is no join between them. But the limit case is very well defined. What you get is a tangent situation, and for that I've drawn this small sketch here where I just want to show you what happens if you move one point to another point. So we consider the join between these 2 points, and you see it more and more approaches a tangent situation, and by definition, for the limit case, when those 2 points really coincide, we assume that the corresponding line is the tangent of that point to that conic where it exactly meets it. So this in particular gives us also the possibility to move a point B really very close to our measuring point E and make one of those lines tangent, we will see in a minute that this is really a useful thing to consider as well. And for that, we now want to define a projective scale on our conic in the following way. So we see that 4 points determine a cross ratio. So if we fix 3 of those points, and we will fix later on point B, A, and D, and we move around C, then this cross ratio here will take all the numbers in R and the value infinity. And to see that even more drastically, I moved to a little more special position here, where I moved my conic to be a circle up to projective equivalence. That makes no difference. I put a line in our picture here at which I will literally measure the cross ratios on the line. And I moved that line in a position such that it's parallel to our line up there, so that the intersection of this line and this line here lies at infinity. And now I will do the usual trick that I do with projective scales. I will label my points here by, well, the points 0, 1, infinity, and 1 point x at which I will measure the cross ratio. And if I do that, it happens that if x is at the point 0, then the cross ratio here will actually turn out to be 0. If x is at 1, then the cross ratio will be 1. And if x is at infinity, then the cross ratio will be at infinity. You may wonder why. Well, the cross ratio between these 4 lines is exactly the cross ratio between the 4 corresponding points here. One of them is at infinity, and that the values of the cross ratio behave exactly like that. We had that already when we were talking about projective scales. So by that, you get an identification of the border of your conic, of the line that makes up your conic, to the real projective line. So each point on the conic really corresponds to one point on the projective line, and this special projection that you have here is called the stereographic projection of a circle to the line. We call it a projection stereographic whenever one point of the projection sits on the curve from which we are projecting. And this point up here really will play the role of infinity. And so you see the cross ratio takes all the values of R joined with infinity, which is our real projective line. So I wrote a little computer program that shows how these points of my projective line correspond to the points on my conic here. So I made an equidistant subdivision of the line here, and I projected those points stereographically to the conic, and you immediately get a corresponding scale on the conic. And if you start to move those points around, you see how the scale changes. So the crucial thing here is that you make an equidistant subdivision on that line here, and if you do so, you can move each of those 3 points to get different kinds of projective scale. So there is a little degree of freedom in your projective transformation from the line to the conic. And we will later on see that this little bit of freedom really corresponds to projective transformations on that line. So with a projective transformation, you can map arbitrary 3 points to arbitrary other 3 points, and these will be projective transformations on the line defining your conic. And this will be our next task to get there. And for that, we have to understand the relation of conics for points on it and the cross ratios they define. So here's the first theorem. Assume that you have projective transformation, and this projective transformation leaves C invariant as a whole. So you take your conic and you take a projective transformation and you consider those that may change the position of each point of the conic, but the conic as such is left as at an invariant place. And if you have that, this induces a projective transformation on the border of C if you consider this projective scale. So to see that, take a conic, take 4 points on that conic, and take a projective transformation tau, which should map the conic to itself. So this picture here, you have to take it not completely literally. I've drawn 2 separate pictures, one for the original conic and one for the mapped conic, but you should assume that those 2 parts of the picture really overlap, so that they really are the same conic in each picture. So if you have that, your projective transformation will map your 4 points to some places. And what we want to show, if it is a projective transformation, that the cross ratio of those 4 points remains invariant under that projective transformation, because this is exactly the criterion for any map being a projective transformation. We proved that in one of our earlier lectures. So we consider the 4 images of those 4 points, and now we claim that if we have a transformation that leaves C as a whole invariant, then the cross ratio of those 4 points here will be the same as the cross ratio of those 4 points. So how to get there? Take 1 point from which we see the other 4 points. So we know that the cross ratio of our 4 points on the conic is the same as the cross ratio of the 4 points seen from an arbitrary point on the conic. So you can use any point on the conic, measure the cross ratio, and that's the value. And you want to show that this is at the end this number. So let's map everything. So if we map, then also our point P gets mapped to a new place. And we know, since this was a projective transformation, that a cross ratio does not get disturbed under a projective transformation. So since it is a projective transformation, we know that if we map all 5 points here, then we will get the same cross ratio. But now we already proved our theorem, because what we have here is the cross ratio of those 4 points seen from an arbitrary point on the conic. And if we have a projective transformation, the incidence cannot be altered. So if a point is incident to the conic before the transformation, it has to be incident after the transformation as well. So our tau of P is a point on a conic, and by this it defines, just by the definition of how we defined the cross ratio of 4 points on a conic, it defines the cross ratio we are looking for, and by that we get exactly the equation we were looking for. And this proves that whenever you have a projective transformation that leaves C invariant, then it induces a projective transformation on the scale that we defined on this conic here. This is amazing. So the proof was extremely simple, but this is an amazing theorem because it ties the conic even closer to our picture of the projective line, while at the same time making a relation to transformations in the embedding space of our conic. So we have our conic. The conic lives in RP2. Now we have a transformation of RP2 that leaves C invariant, and this induces a projective transformation of the space similar to RP1 on the conic. So I consider this as a really great theorem. So now let me approach more or less the converse and consider transformations in RP2, and we want to classify those transformations that leave our conic invariant as a whole. So the points on the conic may move around, that's okay, but they should stay on the conic. And we are interested which transformations of RP2 make such a C invariant transformation. And so for that, let us first do a little experiment. So I've drawn a picture. So our conic here should be the circle here, and I defined a transformation that maps A, B, and C to themselves. So there is a transformation tau that moves A to A, B to B, and C to C, and it should move D to a point tau of D, which is on the conic. And we now look what happens to our conic if I start to move our point tau of D. And what we will observe, there is only one position under which this projective map really maps the original circle that we had here to itself. So most of those transformations will not be tau invariant, and the only situation in which you get such a tau invariant is if you move your point D. We just saw it very briefly here. If you move your point tau D to the point D. So let's come really to that point. If I move it to D, then you see the two conics coincide. And this is what we essentially observe from this situation. Only if D and tau of D coincide, we have a mapping that maps C to itself. So what we will expect if we move 3 points to an arbitrary position on a conic, then for the fourth point, there will only be one position that maps C to itself, that is C invariant under that definition. And this is what we are going to prove next. So let A, B, C, D and A prime, B prime, C prime, D prime be all points on our conic. And now we consider a projective transformation that maps each point to the corresponding primed point. So the images of 4 points define a projective transformation. So if we define a projective transformation like that here, then this is uniquely determined. So now the question is, when does this projective transformation map our conic to itself? And it turns out that it maps the conic to itself if and only if the cross ratio of the points before the transformation is exactly the same as the cross ratio after the transformation. So in a sense, projective transformations that leave C invariant are reasonably rigid things. So if we fix 3 of those points, then the image of the last point is automatically fixed by keeping the cross ratio invariant. So how to prove that? Actually, also this one is not difficult, but it proves a really deep fact. So we consider again one additional point P on our conic from which we observe. And this point is taken to be an arbitrary point. So P can be any point on the conic. And what we will prove that under that condition here, that this point P is again mapped to the conic. By the way, we will prove only the if part here. If you want to have the only if part, you can read it in the book. So what is the idea? Well, very simple. So P is mapped to some other point, and what we have to show that this other point is also on the conic, and this is just a sequence of definitions and statements that we know. So we know that the cross ratio before and after the transformation is exactly the same. So we can write down this equation. Now we know by definition that this cross ratio here is the same as the cross ratio seen from P. And if we now apply the projective transformation, we know by projectivity that this here is also the cross ratio of the transformed points. And now we only have to read this equation. So what happens is we have our points A prime, B prime, C prime, D prime, and we have their specific cross ratio with respect to the conic. And we know that a point is on the conic if and only if it sees these points under that specific cross ratio. And this is what we just proved that happens here. Our point tau of P here sees the 4 points under that fixed cross ratio, and hence it has to be on C. So we proved if we have this invariance of the cross ratio, then P is automatically mapped to another point on the conic, and this means that the conic remains invariant as a whole. So just let me end with a final remark here. You see, if I make a transformation that maps 3 points on a conic to 3 other points, then this is already determined by the property that C should be invariant. And so we can use that to construct projective transformations that leave our conic invariant from the images of just 3 of those points. And we will do that in the next lecture. But if we take that as a fact, then we see that the projective transformations are already determined by the images of 3 points, and by that they behave exactly as projective transformations on a projective line should do. And so once more we get the analogy that the conic itself can be considered as the real projective line, and that the transformations on the conic can be considered as transformations on the real projective line, and that even the fact that 3 points determine the image of such a projective transformation can be carried over to the boundary of our conic here. We will go into more details of how to construct this transformation in our next video lecture. For that, we have to dive into geometric constructions for quadrilateral sets on conics and for harmonic points and conics. We will see that in the next lecture.